Hi, welcome back to Statistics 1. We're up to Lecture 18, and the topic of today's lecture is repeated measures ANOVA. In the last two lectures, we've covered between groups ANOVAs. So in the first case, we looked at a one-way between groups ANOVA, and then we looked at factorial ANOVAs, but again, all between groups. Think back to the independent t-tests. We had an independent t-test where there were separate groups of subjects in the two conditions where we wanted to compare the group means. And then we had the paired samples t-test where the same subjects were measured twice. The independent t-test is analogous to between groups ANOVA, and the paired samples t-test is analogous to the topic for today, repeated measures ANOVA. So I've divided this lecture into two segments. First, I'll talk about the pros and cons of a repeated measures design, because there are a lot of benefits to doing things, to doing experiments in this fashion, but there's also a lot of issues that you have to take into consideration. And then in the second segment, we'll walk through a full example and we'll look at how to do that in R, and then again in the next lab, we'll do more examples of ANOVAs in R. So let's talk about the pros and cons. Before I do that, let me just make it clear, and this should be obvious, that there are some experimental manipulations that just have to be manipulated between groups or have to be manipulated within groups or repeatedly, right? So think of the stereotype threat example. That has to be manipulated between groups. Subjects are either randomly assigned to threat or no threat. You can't then, after you give them the threat condition, then bring them back and have them do the control condition. It wouldn't work. Or sort of more obviously, the polio vaccine example, right? You can't have children randomly assigned to the placebo and then the vaccine. It just has to be manipulated between groups. Likewise, there are some things that have to be manipulated within groups or in a repeated measures fashion, like all the pre-post designs that we've talked about. So in a lot of situations, you don't have a choice. But there are many situations where you do have a choice. And in this first segment, I just want to talk about the pros and cons and things that experimenters consider as they try to make a decision as to whether to conduct an experiment as a between groups design or a repeated measures design. So first, the benefits, or the pros. It costs a lot less. So much fewer subjects are required. And the second point is the most critical point in this lecture. And one of the most important points to take away from an intro stats course is there's more statistical power in a repeated measures design. And that's because the nature of the error term or the unsystematic variance or the chance variance changes. And that's a really important concept that I'll try to drive home here in this lecture. So less costs, it should be rather obvious. Let's take the working memory training example. That initial study that caused a lot of attention and controversy, they actually had 4 independent groups, 4 separate groups of subjects that trained for different amounts of time. So remember, it was 8 sessions, 12 sessions, 17 or 19. And there were 20 subjects in each group. That meant they needed 80 subjects to run that experiment. That's a lot of people, considering that they came to a lab at the University of Michigan, 8 sessions, 12 sessions, 17 sessions. It's sort of common practice that people get paid to participate in these experiments. That's a lot of money. So there's a lot of costs in money and then just in terms of hours of running time. So if we were to run that as a repeated measures design, there'd be a lot of benefits, right? So if we just had subjects do the training and assess them at 8, 12, 17, and 19 days, then we would only need 20 subjects. That's the less cost part. What's more important is it's statistically more powerful because subjects may reveal consistent individual differences across the experiment, right? There may be some people in there who just aren't taking it seriously. And so they're not gaining in the working memory training. They're not going to show an effect of the training. whereas there may be other people who are really working hard at it, and it's consistent across all the conditions. So we can look at that variability across subjects and see if there's systematic variability that we can attribute to the individual people. Remember, in a between groups design or in an independent t-test, any variation across people that are in the same experimental condition is considered error variance. It's unsystematic. Why are they behaving differently? We have no idea. They were given the same exact treatment. What repeated measures allows us to do is account for individual differences, just stable individual differences in behavior across an experiment, which reduces the error term, which increases power. So let me try and illustrate that concept graphically, because again, it's a really important concept and the most important thing to take away from this lecture. So here's a Venn diagram of a variance from the between groups design. So remember, there were just two sources of variance in a one-way ANOVA, the good variance and the bad variance, the between groups variance and the within groups variance. I like to think of it as the systematic versus the unsystematic. So remember, the between groups variance was just variance due to our treatment, or our independent variable A. And the unsystematic was variance within a group. As I just said, why are people within the same treatment group behaving differently? We don't know. That's unsystematic. And the notation, again, is S within A, subjects within groups. Look what we can do with the repeated measures design. We still have that systematic between groups variance due to our manipulation, but the unsystematic variance is now reduced as a function of stable subject variance. So if subjects just reveal stable individual differences across an experiment, then I can attribute that to subjects. And that gets sort of taken out of the error term, and the error term is reduced. The other really critical concept to take away from this lecture is this piece right here, specifically this guy. So the error term in an F ratio is mean squares for the interaction of your independent variable and subject variability. That may sound strange because we just did factorial ANOVA and interactions were not the error term, they were the hypotheses we wanted to test. But if you think about this conceptually, about what error means, it's spelled out right here. Error in a repeated measures design is inconsistent individual differences across conditions. In other words, it's the simple effect of subjects that differ across conditions. That would be an interaction between subjects and condition, right? So that's why I cover factorial ANOVA before I cover this, so you can grasp that concept. So that's the error term. The numerator in the F ratio is still mean square sub A. It's just how much variance did we create due to our manipulation. But the concept and the formula for error is very different in a within subjects design or repeated measures design, and it's critical to understand that point. So here are the formulas for mean squares and F ratio. Nothing new here, so F ratio is just a ratio of mean squares. The only difference, as I mentioned, is we've got mean squares for the interaction of A by S as the error term. Mean squares is always sum of squares over degrees of freedom. So you're just going to see this pattern repeat itself in all ANOVA designs. So let's get to now the downsides of repeated measures. So if you have all subjects participate in all conditions in your experiment, then you have to start thinking about how to order those conditions. In some experiments, that's defined for you, like a pre-post design. But in others, you sort of have to decide which condition goes first and which goes second. So the common approach to solve that problem is called counterbalancing, which I'll explain in a moment. Another big problem, or potential problem, is the issue of missing data. Because you have the same subjects taking part in all conditions. What if a subject just doesn't show up one day? Then you're lacking a full profile for that subject, and that creates problems computationally in the calculation of the F ratio. And there's one more extra assumption that we'll talk about last. So first, let's talk about counterbalancing. If you've had a class in research methods, you've probably heard about this before. So let's start simple. Imagine just a really easy experimental design where there are just two conditions, A1 and A2. And we're worried about the order of them. So one approach is called blocking them. It's a block design. So you just have half of your subjects do A1 and then A2, and then the other half do A2 and then A1. And you just randomly assign your subjects to those two order conditions. And then if you want, you could do a t-test to see if order mattered. But by counterbalancing, you're washing out any order effects that might be having an impact on your main effects. Another common approach is not to block the two conditions, but just to intersperse them throughout the experiment in a randomized fashion. So you do A1, then A2, then A2, then A1. Just make it completely random. Again, do that randomly across all subjects, and you won't have any consistent order effects. So if you suppose we have 3 levels of an independent variable and a block design, then if we want to fully counterbalance, we need 6 possible orders. So we could do A1, A2, A3, A1, A3, A2, and so on. So if we wanted to fully counterbalance and take into account order effects, we would have to have 6 between groups conditions, because they're randomly assigned to one of these, right? So now that's taking away from the benefit of less cost. And it gets worse as the number of levels of A goes up and fast. So look down here at the bottom. If you have 4 levels of your independent variable, then you're going to need 24 order conditions. And if you have 5, you're going to need 120. So clearly this is not a workable solution because, as I said, you're then losing the benefit of running fewer subjects and taking on less cost. So the most common workaround for this is to implement what's called the Latin squares design. So a Latin squares design is not completely counterbalanced, but it makes sure that every condition occurs in each serial position. So let me show you what I mean by that. If A equals 3, then here's 3 ordering conditions that adhere to the Latin squares design. So A1 occurs first here, it occurs second here, it occurs third here. A2 occurs first here, second here, third here, and A3 first, second, third. So each condition occurs in each serial position. So it's not perfectly counterbalanced, but it's pretty good. And it's always going to, the number of conditions number of order conditions you need will always be equal to the number of levels of your IV. So it's very workable no matter how many levels you have. Now let's talk about missing data. So why is missing data an issue here and not in between groups designs? Well, in between groups designs, it was okay to have slightly different numbers of subjects in each condition or each group. So if one subject dropped out of one of the conditions, you have one less subject in one of the conditions, it's not that big a deal. Here it is a big deal because we want to look at people's change over time. And we want to look at the difference scores between 2 conditions. Think of a paired samples t-test, right? If we had a subject who had a missing value for one of the 2 conditions, then we wouldn't be able to use that subject's data because there'd be no paired sample to work with. So this is actually a very big area of research in more applied settings where you're dealing with, say, patient data or collecting data online or survey data or research where you're asking people very sensitive questions that they might not want to respond to. So I'm going to give you a very quick overview. I just want to highlight that it's an important issue in repeated measures. So the one question I get all the time from students and from graduate students, from colleagues doing research is, well, how much missing data is a problem? How much is a lot? And there's no rule of thumb, but to me, like as a reviewer of manuscripts, if I see anything less than 10% in one variable or across the whole project, it doesn't really raise a red flag to me because things happen. People don't show up for the last session of a study, or the computer malfunctions while in one condition. So there's going to be some missing data. More than 10%, and then you start to wonder what happened and why is there so much missing data? To probe that and to try and figure out if the missing data is just random and due to just chance errors, or if it's lawful, there's a really simple procedure. So for any variable of interest, let's call it x, create a new variable, just xm for x missing. If x is missing, then give it a 0. And if x is not missing, give it a 1. Then use that categorical variable, 0 and 1, as the independent variable in a t-test using some other measure, some other variable in your study as the DV. Say you measured age. And you want to see, is the missing data lawful as a function of age? So for example, younger people tend to not answer the question anymore about your ethnic background. Are you Caucasian, Black, Hispanic, whatever. Older people tend to have no problem answering that question. They're used to that. Younger people often just say, I don't like this question. I don't want to reveal this information to whatever agency they're submitting their research to. So they tend to not answer that question. So if you did this, you might see you have more missing values in the younger segment of your sample than in the older. And that would tell you that it's a lawful or systematic pattern. If not, then it's probably just random. So what do you do? Again, I'm giving you a very quick overview of this. We could do a whole nother lecture on this, but the segment's already running long. So one thing you can do is just drop anybody who doesn't have a data point in all your conditions. That's pretty drastic, and you're going to lose a lot of subjects. If you have a lot of data, so if you're just collecting data online, go for it, do that. In the age of big data, this is becoming more viable. But if you're doing something like here at Princeton, we do a lot of fMRI experiments where we put people in an MRI and conduct our experiment. If we miss one data point, we can't just drop the whole subject because it costs $500 an hour to be in that room. So that's drastic. So the other approach is to keep the cases and then estimate that one missing point. And how would you estimate a missing point? Well, there are a lot of approaches, but the most obvious and one that you could think of based on what we've done in this course is use multiple regression. Right? You have multiple data points for each subject. They might be correlated, so you could predict it based on their other values. There are lots of other options sort of beyond the scope of an intro course to go into them. I just want to make you aware that there are options. Finally, the last part of this segment is there's one more assumption, and it's called the sphericity assumption. It's much like the homogeneity of variance assumption. That's part of it. But the second piece is homogeneity of covariance. So imagine we have three conditions, A1, A2, A3. What homogeneity of covariance says is if I looked at, say, the standardized covariance, the correlation between A1 and A2, it should be approximately equal to the correlation between A1 and A3 and the correlation between A2 and A3. That's homogeneity of covariance. There's a simple way to test that, just like with homogeneity of variance. There's Levine's test. Here, there's Mauchly's test. We'll show you how to do that in lab. And if it's significant, there's a quick fix. Again, the worry is that you're inflating the probability of type 1 error if you violate this. So there are adjustments to p-values. The two most popular are Greenhouse Geyser and Wynne-Felt. It's up to you what you want to choose. I always choose Wynne-Felt because Wynne was a professor, a statistics professor where I went to grad school. So I use Wynne-Felt, but they usually give very similar results. So just to wrap up the segment, the pros of repeated measures design: less cost, that's great, but critically, this is the most important point, is it gives you more statistical power because you will most likely reduce your error term because you can pull out systematic individual differences across subjects. The downsides: you have to worry about order effects, practice effects, fatigue. You have to come up with some sort of counterbalancing scheme, maybe a Latin squares design. You have to worry about missing data. And then you also have to test for the sphericity assumption and make adjustments if you violate that assumption.